Okay, well, last time we showed graphically what's represented in this term. We're just summing up the areas of a lot of little rectangles. And now what we want to do, and we kind of drew a parallel between the quantity, the summation that you see here, and the integration. And we showed that what you get when you sum up all these rectangles is a number not too different from what we have when we solve it exactly. But it's a lot of work. We have to figure out the areas of all these individual rectangles and add them all up. So what we want to do now is we want to take a look at this discrete approximation and show how, starting off with something like this, that this leads to the power rule for integration. So we're kind of backing up or pausing, I guess. We've already shown you, right from the beginning of the videos on calculus, how to do it. So I think you already know how to do it. We have something like this, the integrand. We have to figure out what it was that we differentiated in order to get it. Now what we're going to do is show how this summation will help us obtain this rule that we're already using. So we'll just use this function y equal x squared, and to obtain the area, looking down here graphically, we have all these individual rectangles. They're delta x in width. They have a height which is equal to f of x at that point. And so we have a sum, an area which is the sum of all the values of y of I or f of x times this delta x. And however many of them there are, I goes from 1 to n. And we can also write that in this case, since we have a specific function in mind, that this area, right, what we're getting is an area. We're summing all the areas of these individual triangles up. We're getting an area is equal to the sum of x sub I squared delta x. And x sub I squared would just be the value at the midpoint here on this rectangle. So we'll let x sub I then is going to be some multiple of delta x. So we let x sub I equal I delta x. And that gives us that y, then since y is equal to x squared, y sub I is going to be equal to I delta x, the quantity squared. So we substitute that back into our definition, and we have I delta x, the quantity squared, that's I squared delta x squared, times delta x. That gives us an area that's equal to the sum I squared delta x cubed. Well, delta x cubed is a constant depending on whatever delta x is. We just pull that out, and then we get the sum of I squared as I goes from 1 to n. That's something, well, that's, how do we figure that out? Well, fortunately, there are tables of series and functions that help us do that. We have this problem here. Most of us probably can't remember what the sum of I equal 1 to n of I squared is, but that's why we often have books of tables, and now we don't even need the book. We can go directly to the internet. So we're looking for the sum I equal 1 to n of I squared, and we see it over here in the table. And that's equal to n times n plus 1 times 2n plus 1 divided by 6. You can break it down into an expression like this if you like. If we were dealing with x to the fourth, then we'd use this series. And what we're doing when we substitute then back in for the sum of I squared, we have, of course, we're going to have delta x times the sum I equal 1 to n of I squared. That's n times n plus 1 times 2n plus 1, but since n is going to be very large, remember we're letting our delta x go to 0. So n is a large number, 2n is a large number. N plus 1 is basically n. 2n plus 1, basically 2n. And since the number of intervals becomes very large, we can just say n plus 1, approximately n. 2n plus 1, approximately 2n. And that gives us this part of that expression reduces to the sum of I squared equal to n cubed over 3. The 2 cancels out to give us a 3. We have n cubed over here. If we substitute that back into this starting expression, we get delta x cubed times the sum, which is n cubed over 3, this term here, is equal to n delta x cubed over 3. In other words, we're just putting the n and the delta x together. They're both cubed, so we have n delta x cubed over 3. And we'll call this n delta x up. We'll just let it be represented by some big X and over 3. So for some specific value of n, we get this representation, get this reduction, get x cubed over 3. Now, does that start to look familiar? Well, it does. We were integrating x squared, and remember what we have to do is find something which, when differentiated, will give us x squared. So the delta x becomes infinitesimally small and approaches infinity. And the process of integration really saves us an infinite amount of work. We'd have to sum an infinite number of infinitesimally small, narrow rectangles. And we've already noted that this capital sigma becomes the integral sign, and the delta x, as usual with differential calculus, the delta x becomes dx. And the limit then, as delta x goes to 0, of this quantity would be represented as the integral of x squared dx, which we know will be x cubed over 3 plus c. The result of integration in this case is expressed as an indefinite integral. And at this point, I think you can see that a lot of the notation and so on should be looking fairly familiar to you. If we come back and take what we've learned and restate this as a power rule for integration, we go back to the derivative. We use the power rule for differentiation. We bring the power down, reduce the power by 1. We get 3x squared. Divided by 3, that gives us x squared. So using this kind of power rule in reverse, we know that the integral of x squared dx is going to be x cubed over 3. So we increase the power of the integrand. So doing this in reverse, we're increasing the power in the integrand by 1. We get x cubed. And then we're dividing it by the new exponent, which is 3. So we get x cubed over 3. The integral of x squared dx is equal to x cubed over 3. This is an indefinite integral, so we add in the constant c. And this gives us the more general rule. So if we're integrating x to the n dx, what do? We increase the exponent by 1. So we have x to the n plus 1. We also divide the result by this new exponent, by n plus 1. By 3 in this case, by n plus 1 in this case, which is the more general case. So this would be a power rule for integration. So those reverse derivatives and so on that we were doing earlier on, and that you're already pretty good at, again, what they represent is this what we call the integral, and it's giving us the area under this function. So they're just areas under the derivative functions. And again, this you should be feeling pretty comfortable with this notation. We've got some dangling apostrophes in here. Sorry about that. Ignore that. But this term is the integrand. And this is what we have to differentiate in order to get it. So this is the integral. Again, I need to add in the constant c and so on. So hopefully all this is starting to make sense to you, looking fairly familiar to you, the terminology, hopefully sounding familiar at this point. And the next time we're going to introduce some additional rules and just present some examples and work through them. See you next time.